Okay, thanks. First of all, I'd like to thank organizers for inviting me to take part in this wonderful conference. Today, I will talk about a series recent work about the worldwide effective field theory formalisms done with Christoph Dolapa, Gregor Kaelin, Raphael Porto, and Jack Bonif. Yesterday, Raphael has given a beautiful review talk of this topic. So today my talk will focus only on technical aspects complementary with his. Let me start with two historical breakthroughs in science that happened in this century. The first one is the discovery of Higgs boson from the Large Hadron Collider in 2012. And the second one is the first direct detection of gravitational waves from merger of two black holes by LIGO recently in 2016. These two historical events marked that the fundamental physics, including high energy physics and gravitational physics, in the new way, and the new precision era. In particular, so gravitational waves provide a new way to test the general relativity. For this purpose, precision theoretical prediction is very important. Together with Raphael's talk, so I will convince you that modern tools from particle physics and mathematical physics are playing a crucial role in study precision gravitational wave physics. So as we know, so binary black hole or binary neutron star systems are primary sources of gravitational waves that can be detected by the current detector like LIGO, Virgo, Kagra, and LIGO India, as well as upcoming future detectors such as LISA and the Einstein telescope. So as shown in this picture, evolution of a binary black hole system consists typically three phases: in spiral, merge, and rain down. And for rain down phase, the black hole perturbation theory works perfect. And for merge phase, the interaction is extremely strong, and Einstein equations are linear, highly non-linear. So we can only use numerical simulations to solve problem in this phase in general. For in spiral phase, it costs a huge number of cycles. So if we use numerical relativity simulations, it quite computational expensive. But in this phase, the interaction between two bodies is weak, and so the relative velocity between two bodies is very small. So perturbation theory works. For example, we can compute a correction order by order in V. So that is Feynman's post-Newtonian expansion. Similarly, we can also organize our computation in an expansion in Newton constant only. So that works for any values of velocity. So this is so-called post-Minkowski expansion. And quantum field theory method, so is combined with modern loop integrals, works very well for, in particular, post-Minkowski expansion. This is also main scope of my talk. So because of in spiral phase, so the size of bodies is much smaller than the distance between two bodies. So we can use point particle approximation to describe a black hole or neutron stars. We can just use this action. This is just the action for non-spinning particles. And here we can also, as mentioned by Raphael yesterday, we can also add more terms to describe tie-dye effects and spin effects. And the two bodies, the interaction between two bodies is described by Feynman's Einstein Hilbert action. In in-spiral phase, as shown by in Emil's slides. So in this case, the matrix can be written in terms this way. This is just a small fluctuation around the flat space. This fluctuation h mu nu describe just gravitational fields. So the basic idea behind in our formalism is that so using ideas from effective field theory, so we can construct effective actions for binary systems via integrating out gravitational fields from full action. So to compute effective actions, we can use perturbation theory. For example, we can expand everything in powers of Newton constant. It's just a post-Minkowski expansion. Here, so the leading order is just describe so the motion of free particles, and higher order describe gravitational corrections. Notably, in our formalisms, we do not do path integral for word-like degrees of freedoms. Instead, for trajectory, we just solve classical equation of motion directly, order by order in G. And from equation of motions, we can compute physical observable like impulse. It's defined as the change of momentums from final states to initial states. Because second term is the total derivative terms, so only the first term contribute to delta p. So because we are interested in only classical physics, so we can use saddle point approximation to keep only classical contribution. So in particular, for example, in our calculation, we do not need to consider diagrams with graviton graviton loops, because they are pure quantum gravity effects. As a result, so this EFT formalisms enjoy both advantage of pure classical physics and QFT method. Because with QFT method, we have a systematic and efficient way to do computation, and because we care about only classical contribution, so we can we keep only classical contribution. That makes every step simplified. So in this slides, I want to show you how our effective field theory framework works. So this is just the simplest diagram. It's a tree diagram. It's just a graviton line connects two word lines. So from this diagram, so it's straightforward to read out effective action use Feynman rules. So from these effective actions, we can immediately write down equation of motion for trajectory, just like this. Here I just take a free part of trajectory into right-hand side to keep only leading order contribution. And from first line to second line, we just perform an integration for tau2 from -infinity to plus infinity. That just gives Dirac delta functions. And if we integrate out equation of motions, we can get the velocity and the positions for trajectory. For example, this is a velocity. This is position trajectory. This is a free part, and this is a leading correction. And here we can say this procedure naturally needed to lead to a linear propagator. And here we must include a small imaginary part to ensure this correction vanish in the boundary. So, and with effective actions, we can also compute the inputs. It's given by these formulas, and this formula is exact in any order. And if we only plug free part of trajectory into this formula, we get a leading correction for delta p. It's a purely Fourier integrals. So we can get the final result by a simple algebra. And if we take a leading correction from equation of motion, so we can get a high order, for example, we can get next to leading order, means 2 p.m. order, a correction for delta p. So it's a twofold momentum integrals. One fold is from this formula, and another fold is from this correction. So finally, result has this form. So in this form, this is the Fourier integrals, and this is the one-loop scalar integrals. So this example is very simple, but it captures the general structures for delta p at any order. Yeah, for example, so at 2 p.m. order, we also consider like these diagrams, and this one contributes to 3 p.m. order, this contributes to 4 p.m. order, and this contributes to 5 p.m. order. And it's any n p.m. order. So the inputs delta p has this structure. So this is just the Fourier integrals that transform a result from the space of impact parameter to the momentum space. And this is n-1 loop, scalar integrals. And here, D1, D2, D3 just a graviton propagator. So it can be retarded form in informalism. But if we are interested in only conservative contributions, we can simply use the Feynman form. And very interestingly, if we want to realize local in time and non-local in time separation for conservative path, well, we have to compute integral with log omega. This log omega just from non-local in time radial action. So it's defined. It's defined as the energy in the center of mass frame. So it has a highly non-trivial dependence on mass ratio. So now I have shown that so the K to solve two-body problem within two-body problem within quantum field theory approach is to compute Feynman integrals like in this form. So and now I will introduce some general property for these integrals. So first of all, for these integrals, for each loop momentum, there is always a delta functions in this form. The argument is linear in loop momentum and one of velocities. And this integrals depends on 3 external vectors. Q is momentum transfer, and U1, U2 just the initial velocities. They satisfy these relations. So if we do not consider this part, this integral is a function of single visible gamma for any order. So if we need to consider this part, integral has a non-trivial dependence on mass ratio. So now, so therefore, multi-loop technology from particle physics can be directly used to solve gravitational wave problems. Now I will introduce some useful useful tools from particle physics. So first of all, for delta functions, because of these relations, we can replace delta function by Carter propagator. It looks like just a linear propagator, but but the index cannot be negative. And for this log terms, if we introduce a new parameter like lambda tilde, if we expand this quantity around a small tilde epsilon, so we just found that the linear term, that means the second term, just the log term. So because of this, we can use this replace logs as a result. So our integrals becomes ordinary integrals in particle physics, but the cost is so this propagator has a non-integer index. So therefore, the standard loop integral techniques can be swiftly used to compute integrals in gravitational physics. So firstly, because in practice, we have to compute a large number of integrals, but in general, they are not independent because of integration by parts identities between them. For example, if we consider these quantities, this is a total derivative. So it vanishes in dim right. But if we perform this derivative and expand this quantity, we can find every term can be written in term as an integral with different indexes. So as a result, so this relation generate a system of homogeneous linear equations. So to see this, let's say a very simple one loop examples, just this. If we take three here, so this vector has three different choices. So that gives three sets of equations. And for this simple case, we can solve these equations analytically. So finally, we found if first index is even number, it's 0. Because this is simple, because from this equation, the second equation just link integral with I1 plus 1 and I1 minus 1. From here, we can say, so this index can be reduced to 0. If first the index takes 0, this integral is 0 because this propagator is a cut. And for all case, any integral can be reduced to only this integral. So for this case, we can say any integral can be reduced to only one integrals. This is called mass integrals. And in general, for more complicated cases, by solving linear IPP equations, we can always write an integral as a linear combinations of a small number of base integrals. This is called mass integrals. And for high loop cases, it's almost impossible to get symbolic solutions like this one loop example. But fortunately, because this is very important, so many advanced technology has been proposed in particle physics, and many of them has been implemented into computer problems. For example, this is some publicly available problems include such as reduce fire, nitrate, Kira, and finite flow. And very interestingly, so some new recent development looks very impressive to push forward this field. Like need IVP is the first implementation of algebra geometry method. With after reducing integrals, we have to compute a set of mass integrals. For this, it turns out the method of differential equation is a powerful way to evaluate master integrals. The idea is very simple. For example, for a set of mass integrals, if we do a derivative without some canonic variables, so we can get a combination of integrals. Normally, they are not mass integrals, but using IP relations, we can pull them back into mass integrals. So finally, we can get a set of differential equation in this form. This is just a matrix with element with rational functions in X and in epsilon. Epsilon is just Dirac regulator. So important development in this field is so you about 10 years ago, Johansen observed if we find a proper transformation for master integrals such that so for new basis, if differential equation matrix gets simplified, means so epsilon dependence can be factored out from this matrix. So and then we can write down answer order by order in an iterative way like this. Furthermore, if this matrix has only simple pairs in X, and then so solutions can be written in terms of iterative integrals, or namely multiple polar logarithms in any order in epsilon. So and for this case, Li has proposed a complete algorithms to find the canonical basis automatically. Now several computer program works for this purpose. So because in polar log cases, because polar logarithms is a large classes of functions appear in Feynman integral calculations. So in this slide, I gave a brief introduction to polar logarithms. So it's defined in a recursive way in this formula. So the most important property is so it has only simple power. And this definition starts from this one. And for special case means all arguments A1 to AN is 0. It's just a log or log square, log cube like this. And this MPL contains the well-known classical polylogarithms. It's just special values of MPL. And if these arguments take only 0 or -1 +1, in this case, polylogarithms can be reduced to harmonic polylogarithms. An important properties for logarithms is that is transcendental weights. It's just the number of iterated integrations in this definition. So from here we can say, so for rational numbers it's 0, and for logs can be written in terms of one-fold integrals. So it's 1, and for zeta n, because zeta n is special values of classical logarithms, so it's n. And for pi, it's 1 because pi square is related to zeta 2. So now I show you example example of using canonical differential equations and polylogarithms. It's our calculations at 3 p.m. order. In this order, as mentioned by Raphael yesterday, we just need to consider only 7 diagrams. Here I show 3 representative ones. And in this order, the case to compute the integral like 2-loop integrals like this. And we found for non-spinning case, when we by doing IPP reductions, we found we need only 8 mass integrals. So we can easily transform into canonical differential equations like this here. So A, B, and C are just a constant matrix. And from here we can see we have only x equals 0 and x equals -1 and +1 3 poles. So in this case, any integral can be evaluated into harmonic polylogarithms. And with the result of integrals, we can compute observables. So for inputs, we found the final result need only weight 0 functions and weight 1 functions. This is equivalent to log. This is just the log x. But from 4 p.m. order, so more complicated function will appear beyond the polylogarithms. For example, we also managed to compute to solve differential equations with elliptic case. For example, this is the example appear in 4 p.m. calculations. So at leading in epsilon order, this equation has this form. So we can transform it into, this is the 3 first order differential equations. We can transform it into a third order differential equations in this case. And for these equations, we just found it's very easy to find the solutions. For example, simply using mathematical. And the 3 solutions are in terms of complete elliptic integrals K. So with this canonical, we may transform this block into epsilon factorized form. But here, unlike a polylogarithm case, so elliptic integral appear in transform matrix for differential equations. This can be found by initial algorithms. So if we get this form, we can try to construct general solutions for high order in epsilon. They are normally iterated integral involving elliptic kernels. So now with general solutions for differential equations, the last sense is to determine this boundary constants. So for boundary constants, as Emil just mentioned, so we just use method of ranging. Because of our formalism is pure classical, so we have no hard ranging that contribute to quantum effects. So classical soft ranging so can be furthermore separated into potential ranging and radiation ranging. So potential ranging is just defined in this way, means for potential modes, its component, energy component, and the momentum energy component is much smaller than momentum components for its momentum. term. And for so potential modes are purely space-like, but for radiation modes, so it's ionic components and magnetic components has the same size, so it can be on shear. It's light-like. So then I will use a 4 p.m. example, means a 3-loop integral, to show how this method works. So, for example, for this complicated integrals, so for convenience, we just relabeling loop momentum for this three lines, and perform a comprehensive analysis. We found four independent regions. So the first region is the potential region, means three loop momentums are in potential region. And we found two types of this kind of regions that has one radiative modes and two potential modes. And we also one region that has two radiative modes and one potential modes. So we can also do this in particular for Feynman propagate case in Feynman parameter form. In this case, we can use mathematical package ASY2 to do this. We check this. It is consistent with our analysis in momentum space. So with this technology, we can explain the integral in near static limit according to different region for momentum for different behavior. So this is our result for potential region. So integral is simply reduced to d-1 dimension integrals. And for this case, so this is a potential, but for this part looks like looks like a one-loop integral with a mass term. This is similar, and for this is twofold. And for this kind of integrals, we can further do, for example, do IB reductions, and then we can compute them using the method of direct integrations. So very interestingly, we found all regions add up leads to a finite result, in particular IR divergence cancel. This is a highly non-trivial property. So with result for integrals, as Rafa shown yesterday, so we can compute a full impulse at 4 p.m. order. So it includes conservative effects and deceptive effects. In this result, it contains the rational function log, dialog, and elliptic integrals. So this is the first full result at this order. So as Rafa pointed out yesterday, so the full result cannot be used to describe a generic elliptic-like motion because of non-local in time effects. So as shown in previous slides, so for 4 p.m. at 4 p.m. order, if we want to compute non-local in time effects, we can construct integrand from 3 p.m. diagrams like this, because of there is an overall defect in non-local in time radio action. So, and then using trick, I introduced before, we just treat this one as ordinary propagators. but with a non-integer index. And then we found the IP can be done using a public available a package like Litrate and find flow. Finally, we found the 17 mass integrals. So in this case, result depends on both gamma and mass ratio. And because of this reason, so result is much complicated compared to the full result case. So for example, it logarithm sector. So many complicated functions can appear in arguments. So and in this case, complete elliptic integral as well as iterated integral of elliptic kernel appear. For example, this is some of iterative integral of elliptic kernel appear in our result. So the definition is completely the same with for logarithms, but the kernel has much more complicated analytical structure. So in our result, we have like this. This is one-fold integrals, and this are two-fold integrals. So this is definition of kernels. It contains it in terms of elliptic integral k. So we just found so for example in this one, so in divergent terms it's complicated, but their combination has a simple post-Newtonian expansion, and we found so all kernels have at most simple pairs. So that means it's easy to evaluate, in particular in self-force means small Q expansion. Let's show you an example. So for example, for first integrals, so it's very easy to compute to expand in mass ratio Q, and at each order, the result is simple. It has only simple power. And then so integrate out is straightforwardly. So instead, we can also do Q expansion before IBP and compute integrals. We just straightforwardly expand this in terms of Q. Finally, we get this result. This term is trivial, but for this term, it's real Q expansion. Now, the independence of Q is factored out, but the cost is we introduce a term with higher both numerator and denominator. But good thing is so they becomes ordinary two-loop integrals. In this case, we found using a new version of K-RA, so it works very well to very high order, like this is very high. So with result of the integrals, we obtained so non-local in time contribution to scaling triangle. So this is also shown by Raphael yesterday, and in this result for coefficients HI, so we provide the exact in mass ratio case and the self-force expansion versions in our recent paper, and this result is perfect agreement with so 6-pin result obtained by Bini, Damo, and collaborator. And also, Raphael pointed out yesterday, so using this result combined with the 6-pin result in this paper, we can obtain an improved bound Hamiltonians. That is important for real gravitational wave physics. So now I conclude my talk. So in conclusion, modern techniques from applied physics and mathematics physics have already proven very useful to solve gravitational two-body problems. And together with Rafa's talk, we can conclude post-Minkowski dynamics can be nicely bootstrapped from post-Newtonian physics. And so in past few years, we have developed an efficient framework and obtained full results to next to leading order, means 4 p.m. order, including conservative parts and deceptive parts. And we also realized local in time and non-local in time separations. Finally, I conclude my talk by an outlook remark. So as mentioned by Rafa yesterday, so the future discovery potential is gravitational observation highly rely on so the precision of our theoretical predictions. So next to leading order means 5 p.m. order is highly desirable for next generation gravitational observations. So in this direction, as I just showed you, so our recent method for 4 p.m. Looks very promising to compute non-local conservative dynamics at this order. And for full result at 5 p.m. order, so we can organize into a self expansion. It contains three kind of terms. This case is just the proper limit case. It's trivial, and this is linear case. This is a second self-force contribution, and this is second order contribution. So very recently, so Homburg's group, led by Jan Plewka, reported the result for conservative dynamics at 1 SF order. And in future for 2 SF order, so it's very challenging because so first in this order, so a non-planar diagrams appear for the first time in post-Minkowski gravity. And secondly, so in this case, it is expected that more complicated functions appears. For example, so recently 2 groups analyzed some integrals. In this case, they found so in addition to logarithms, there are also integrals over elliptic curves and Clavier manifold. But one interesting observations from this paper is that so some elliptic integrals appear in calculation of integrals, but it doesn't appear in physical observables because it's just appear in high epsilon order. So maybe these properties happen in 2f order. We need more investigation. So another interesting direction is scattering waveform. So recently, so some groups has paid a lot of attention to compute next to leading order waveforms. So for next to leading order, so we need to compute 2 loop 5-point integrals like this. This is a planar diagram, but this is a non-planar. So this is very challenging. But interesting thing is that recently, so a breakthrough in particle physics is that 2 loop 5-point with 1 mass integrals was obtained by very recently. So this may be useful to compute integrals in classical scattering waveform. In conclusion, so we need a new technology to push forward the precision frontier. Thanks for your attention.
Thank you, Dr. Liu, for a very interesting talk. And so we can have some questions now. You can raise your hand and ask your question now. Yes, any questions, please?
I have a quick question. So in the 4 p.m. at 4 p.m. It's
Yes.
The complete calculation is known, right? You don't need to do a SF expansion. Do you at 4 p.m.?
4 p.m.
So this is the final complete result, right? This is the complete result at 4 p.m.
Yeah, it's complete. It's complete.
And 5 p.m. you are saying only up to 1 SF it is so what that?
Yeah, one SF conservative part.
I see. And also at 4 p.m. This has been, if this radiation reaction, these things are included at 4 p.m. order.
Yes, this result contain radiation reaction effects.
I see.
Yeah, in this paper. Oh, no, this.
I see. I see. And these are non-spinning, right?
Yeah, it's non-spinning.
And for spinning case, how far this kind of computation has been this kind to which PM order?
In principle, it's straightforward because integral result can be directly used to compute the spin case, but for spin maybe Lorentz algebra means integral construction. It's more complicated than non-spinning case a bit.
Thanks.
Yeah. Okay.
Okay, so are there further questions? Okay, so if there are no more questions, then let's thank Dr. Zhengwen Liu once more for a very nice talk. And our next speaker